Today what we're going to look at is paper 2 from 2019 AQA, the AS Physics. So this is the practical skills paper, and then a section of multiple choice. So like last time, I'll do each individual question as its own video, and then I'll do the multiple choice probably in chunks because there's quite a few of them, but they're not enough for like a video each. So uh, question one. This question here is based on the experiment using diffraction grating to determine the wavelength of light. So we've got diffraction grating, we've got 5 spots of light, and they measured 3 different distances. They measured uh, A, B, and C. Okay, and they're all labeled there for you. So it uses a meter ruler with 1 millimeter divisions to take the readings. He uses these readings to obtain A, B, and C. So he estimated his uncertainties at 2 millimeters. We've got our readings there. Okay, so question 1-1 is explain why the estimated uncertainty in measurement A is greater than the smallest division on the meter ruler. You should refer to readings taken by the student in obtaining this measurement. Okay, so when dealing with uncertainty, especially with analog instruments, okay, um, you have to um, take into account um, not just your uncertainty of based on the resolution, which often we would say the uncertainty is plus or minus half the resolution, or sometimes plus or minus one of whatever the resolution of your measuring device is. But you've also got the fact that um, determining whether or not you're measuring the center of a dot. So here it's a dot. So you're measuring center to center. But if you don't have or if you don't know exactly what center, so you kind of you put that in there uh, as well. So for something like this, it's not unreasonable that for one measurement, you would say that your uncertainty is your resolution. I mean, I wouldn't say that if my resolution was 1 centimeter, it would be, I would still estimate it to be a little bit less, but my resolution is 1 millimeter. Uh, and in this case, the uncertainty of your positioning is also 1 millimeter. Okay. And then combine that with the fact that you are making 2 measurements. You're measuring here and you're measuring here. That those two uncertainties add together. Okay. So So again, if our uncertainty in measuring a specific position or a specific dot is 1 millimeter, that's what that's what it is, and it has to do with the fact that, again, like I said, resolution of your measuring device. It's an analog device measuring the center of your spot. Same thing. So you have to add together you have to add together your uncertainties. Okay, and you'll notice that actually, like the uncertainty, it's still an estimate of your uncertainty. But it's what we're going with. Okay, so this is good. So what we have to do is we have to look at percentage uncertainty. So our absolute uncertainty, you add, because we're adding, you add absolute uncertainties. That's how adding works. Or adding two values together, how it works. So A plus B, 289 plus 255. So 544. Our uncertainty is 2 millimeters plus 2 millimeters is 4 millimeters. So our percent uncertainty, 4 divided by 544 times 100. It's a little bit less than 10%, probably around 8%. Oh, no, never mind. Sorry, 0.8%, 0.7%. How many sig figs should I use? Definitely got to be more than one. Oh, but definitely no more than two. All right, 0.74%. Okay, so this is just about how you deal with uncertainties. So uncertainties, when you're adding, you add together absolute uncertainties. If you're multiplying, you have to convert absolute uncertainties into percentage uncertainties, and then you add percentage uncertainties when you are multiplying numbers together. So um, adding numbers together, you'll change your uncertainty, but if the numbers are relatively similar, not by very much. However, when you multiply numbers together, oh man, your uncertainty starts to go through the roof. Um, Same thing if you're dividing, because dividing is just multiplication, as well as if you're taking exponents, your uncertainty gets much, much worse. However, if you take a square root or a cube root or something similar, you will end up with less uncertainty just because of the way the math works. So, again, this is about it. So it's you are adding two uncertainties here. So you're adding two absolute uncertainties. You've got basically it's A plus B involves four measurements. Okay, so you have four different measurements that are adding to this uncertainty, whereas C is two measurements. Okay, so the fact that you've got only two measurements versus four measurements, it means that you're going to have less uncertainty. Okay, um, and basically because C is larger, okay, you're going to have uh, a much higher or much sorry with C you're going to have a much lower percentage uncertainty because you're measuring across a larger distance. So your uncertainty in any one measurement, it's going to be constant. And so if you're measuring over a larger area, you're going to have less uncertainty. It's why when we're doing timing things, you have to do if I'm trying to measure the period of a pendulum, I'm not going to measure one swing of a pendulum. I'm going to measure across 10 swings of my pendulum or more if if I've got lots of time. Because the larger your measurement is in relation to your uncertainty, the less, the smaller percentage uncertainty you're going to have. And that's really kind of what we're looking for, is having a small percentage uncertainty. Okay. Um, so I would probably back this 2 marks. This is probably only worth 1 mark, but I've written here. I think I'll show you that C's percentage error. So here we have 2 divided by 544. That's convenient. Uh, 0.37%. I don't even have to math it out. It is half of it's half the uncertainty. Okay, so that's the kind of thing that we're looking for in a question like that. So 1.4, eye protection should be used to prevent eye damage when using the laser. Describe one safety measure to minimize risk to eye damage when using the laser in the laboratory. Okay, so don't say eye protection because it's already telling you eye protection. Read the question. Okay. Um, so, I mean, basically, it sounds dumb, but you could just say, don't aim the laser towards people. So always do your experiment, so that you're behind the laser. Um, don't look directly into the laser. It's weird. This is one of the weird ones where you can do sort of what feels like a GCSE answer, but don't look at the laser. Um, the other thing that you can do is, you have to watch out for the reflections off the diffraction grating. Um, okay, and the thing is, you need to be careful about how you're phrasing it. Um, about the fact that you are looking into the laser. It's not looking at the laser, so it's into the laser. So it's the laser beam itself. The laser, whether it's a laser pen or it's not the laser that's the problem. It's the laser beam, the laser light. So don't look directly into the laser, not directly at the laser, because those are different meanings. Okay? So, all right, 1.5. This one is actually a knowledge one by the looks of it. Okay, well, we know that this is 0.544 meters. So just a tangent. Four divided by 1.280. And then we inverse tan that. And we've got about 23 degrees. Okay, not really an issue there. That should be pretty straightforward as long as you know geometry. Okay, spot E is a second order maxima. Diffraction grating has 3 times 10 to the 5 lines per meter. Calculate the wavelength of the laser. Okay, so straight to our formula sheet. D sine theta is equal to n lambda. Now, we cannot make the assumption that tan theta and sine theta are the same here. The reason being that it is not an angle less than 10 degrees. So we actually have to work backwards, but it shouldn't be too difficult. The only thing is, remember, this is lines per meter, not meters per line, so you need the inverse of this for D. Okay, so okay, just do a little bit of simple algebra there. And so we end up with 2 over 3.00 times 10 to the 5. That is times sine 23. No, that's not right. I have to just divide all that by 2. 6.5 times 10 to the minus 7, or 65 nanometers. 6.5 times 10 to the minus 7. 6.5 times 10 to the minus 7. Yeah, 650 nanometers sounds about right. I'm going to go 6.51 for the sig figs. Okay, good. And our last question for this question. Student plans to repeat the experiment using the same diffraction grating and laser state and explain one way the student can change the experimental arrangement to reduce the percentage uncertainty in the measurement of the wavelength. So, well, basically the important thing is you would increase distance y, and that'll lower your percentage of y, and then you would have to then that leads to an increase in c, okay, because theta is constant. Okay, so if we got a bigger y, we're going to have a bigger c, which means that the percent uncertainty, I apologize for my handwriting, but I mean, I've taught you guys for long enough, you know. So that's a lower percent uncertainty in C, because your uncertainty from your ruler is not your absolute uncertainty, is your absolute uncertainty is your absolute uncertainty. That's based on your measuring device and your measuring technique. Your percent uncertainty depends on what you're measuring. So by increasing y, we're going to have a lower percentage increase or percentage in y, and therefore we'll have a smaller percentage for this here for C. You could also choose a higher order, Or you could do something like measure the distance between A and E, because anything that increases the distance that you are measuring will lower your percentage uncertainty. Okay, so it's all about measuring something that is larger. Okay, that will lower it. And that does it for this question.